Hi friends, welcome to my YouTube channel. Today we are going to discuss about contact pressure distribution. So the upward pressure due to the soil on the underside of the footing is termed as contact pressure. Okay. The contact pressure is nothing but the upward pressure due to the soil underside the footing. Okay. This is the pressure because of the soil that is underside the footing. This will cause some upward pressure to the footing. So this will vary depending upon the type of soil on which the footing is present. Okay. So depending upon the clay or sand, the material type, this will be varied. Okay. So this is a very important question in most of the competitive exams, as I myself observed this a lot in most of the question papers. So they will just be confusing us with various diagrams and terminology, but here I will help you learning this in a simple way. So coming back to the topic, we are talking about the contact pressure on saturated clays. Okay, first we'll talk about the saturated clays. Figure shows the qualitative contact pressure distribution under flexible and rigid footings resting on saturated clays and subjected to UDL-Q. See, whenever we are analyzing any structure, we will take the load acting as UDL, that is uniformly distributed load. Whatever the load is acting, it is not a point load or it is not a concentrated load. It would be rather be UDL. Okay? Yes. Coming to this, when we are just assuming the load of Q kilonewton is acting on that kilonewton per meter as it is in UDL. Okay. So taking the saturated clays, this is how the contact pressure distribution diagram will look like. Okay. So remember, whenever we are talking about clays, the material distribution diagram would be from end to end. Okay, whatever it is. In this we have flexible footing and rigid footing. For flexible footing, it would be like a deformed beam direction. Okay. It would be same as a deflection diagram. Okay. But whenever we are talking about the rigid footings, it would be like this. It would be something like this. Okay. Yes. When the footing is flexible, it deforms into the shape of a bowl with the maximum deflection at the center. Okay. It is in the shape of a bowl where the maximum deflection observed is at the center. And the contact pressure distribution is uniform. See, here we are seeing it is uniform. Whatever the variation over the length of this is there, that is uniform. Okay. But coming to the rigid footings, the settlement is uniform. The contact pressure distribution is minimum at the center and maximum at the edges. See, we should just remember this diagram. Whenever we are talking about the flexible footing in this saturated clay, it is maximum at center and minimum at ends. Where it is vice versa in rigid footing, that is, it is minimum at center and maximum at ends. And also we have to remember this diagram. In many exams they will first show us the diagram, but whenever the diagram is not possible, they will ask us like where is the maximum stress and where is the minimum stress. Okay, this would be asked most frequently in our upcoming videos. So this is the contact pressure distribution on a saturated clay. Okay, coming to the saturated clay, we have flexible footing, rigid footing. This is a diagrammatic representation of the stress distribution. And also we have maximum at center and minimum at corners for flexible footing, and minimum at center and maximum at edges for rigid footing. Okay. Next we'll go to the second type of sand that is present below the foundation. This is the contact pressure distribution on sand. Whenever we are talking about the clay soils, that is the previous type, but we are talking about the sand now. The below figure shows the contact pressure distribution under rigid and flexible footings resting on the sandy soils subjected to a UDL of intensity Q. See, here the basic assumption, the initial assumption is same. That is, the material is subjected to semi-initial UDL, okay, which is again of intensity Q. So the edges of the flexible footing undergo large settlements than in the center. Okay, that is here it is opposite to that of the elastic, that is clay soil. Okay, whereas in the clay the flexible one was having the maximum at center and minimum at edges, but now it is the vice versa. That is, the edges in this flexible footing will have more settlements than compared to the center. This is the diagrammatic representation. Okay, but that is, the soil at the center is confined and therefore has a higher modulus of elasticity, that is E, and less at the center, and deflects less for the same contact pressure. See, all this we are assuming that the contact pressure is same. Whatever the 4 diagrams we have drawn in clays and sand, we are assuming that the initial condition is that it is subjected to a UDL of intensity Q, and also the contact pressure is uniform in all the 4 conditions. Okay, so the soil at the center is confined. Confined is nothing but fixed, that is, it is restrained. So the higher modulus of elasticity, so therefore has higher modulus of elasticity. See, when I am talking higher modulus of elasticity, where highest elasticity is nothing but the ratio of stress and strain. So the strain is nothing, whenever these modulus of elasticity is high, this strain is less. That is, I am saying from this condition the modulus of elasticity is inversely proportional to strain. Okay, inversely proportional. So that means whenever the modulus of elasticity is increasing, the strain is decreasing. That is why I told you, like in center we have high modulus of elasticity, that means less strain, there is less deformation over here, and edges we have more, so that means strain is more, and deflects less for the same contact pressure. Okay, deflection is less. Okay, this is the basic condition, whereas the Young's modulus or the modulus of elasticity is inversely proportional to strain. As here in the center we have high modulus of elasticity, the deflection over here is very less compared to that of the edges. Okay, for C5 soils, the contact pressure distribution will be intermediate, that is between the extreme cases of A and B. Here we have some extreme cases of both A and B. So C5 soils will have some intermediate one, that is in between both these A and B conditions, or I can say it is combination of both of this. Okay, the contact pressure distribution depends upon the degree of rigidity. How rigid the material that is carrying the foundation is will contribute the contact pressure distribution, will contribute to the contact pressure distribution. However, in most of the practical cases, the assumption of uniform contact pressure distribution yields sufficiently accurate design values for moments, shears and vertical stresses, and hence freely or safely adopted. Okay, in this we are saying that the basic assumption, whatever the contact pressure is there, that is uniform. So that was our basic assumption. Because of this assumption, whatever the accurate design values we were getting, that are suitable also for the practical conditions, for moments, shears and also for the vertical stresses. So we can safely adopt all these values, or the diagrammatic representation whatever shown here is correct. Okay, so that is it for this video, guys. Please like, share, comment to my channel. Please subscribe to my channel, that would greatly help me. I appreciate you watching this video. Thank you.